to speak about the pH zone refining CCC. So why the pH zone refining CCC called the efficient preparative separation method for natural product? Because this method can purify the gram quantity of the pure natural product during the one-step separation from the crude extractors. So this, I'm going to skip the few slides because the other speaker already talked a lot about this, so I don't want to spend too much time on here. So CCC, I like the Dr. Juice compare the CCC. He described CCC as a bicycle, he said. Also, if HPLC like a car, we don't want to competing with HPLC in the highway, you know. But in the world, you have a lot of narrow road, so car never can reach. So CCC is maybe the best way, the bicycle maybe the best way to get some small road. So also, like the natural product, is CCC the best way, maybe not the best way, but it's a very good way to handle the dirty crude extract from the natural product. So I think the CCC have it all advantages compared with HPLC. So this is the instrument. Is a prototype instrument developed by Dr. Ito in his lab. I think a lot of commercial companies copied this model and they have a lot of commercial and available now. In this, okay. So this instrument contains the 3 multi-coil columns. You can see from here, this is one column, this is another one is on the back, one is rotated. So this column can hold about 1.6 liter total capacity. So, but this column can be changeable. You can make the smaller amount too. You use a different size of tube. So most of the separation I'm going to introduce here is use this instrument. So this is a G-type motion for the CCC. I don't want to talk about anymore about this. Dr. Conway have a nice model showed you last time how this motion works. So I just want to say this. Like this is a J-type anti-twisting design. So Dr. Conway also demonstrated this with the dancing with Dr. Leto. You can see how it can be works. The mechanism is very simple. But this design, you know, Dr. Ito have almost 100 patents. His patent resulting about more than 10 commercial CCC instruments. But none of this instrument has been making money for NIH or even for himself. But this design was used for the blood separation. This was because for the old design of the blood separation, they use the rotating seal. You know, rotating seal is a very expensive device. You cannot discard it for each people, one-time user. So they use this design for the blood separation. You can, when you donate blood, the partially donate the blood, you can use one tubing after centrifuge. They take out the parts they want. Other parts can be sent back to your body. But you don't want to use a rotating seal with this device. This causes cross contamination. So they use Dr. Ito's this anti-twisting design for this blood separator. So this because this is a large scale, lot of used for in the world. So it make millions of dollars for NIH. Also, Dr. Ito also got some profit for it too. So that is the only case one that I cannot say the only one, but that patent make some profit. So okay, I want to escape this slide because Dr. Conway showed use his model. Also, Alan showed the movie how this works. I don't want to speak more here. So then we go back to the pH zone defining CCC. So in this part, I'm going to talk about how this method was found, also the mechanism, and the most important part, I will give a lot of examples for its applications. So this is experiment did by Dr. Ito in his lab. So he found the first slide in this chromatogram. He found unusual sharp peak after he purified the two compounds. This is a bromine acetic T3 is a kind of dye, is acetic dye. So this compound, this is the impurity. He found the peak eluted late is much sharper than the peak eluted earlier. This is unusual for the CCC chromatography. Most of the chromatography should be early peak is sharp, late peak should be bolder. So in this one, he calculated the theoretical plate. First peak is like 800, is normal for regular CCC, but the later peak is about 2000. It's very unusual for CCC, for this peak. Then he tried another solvent system in this chromatogram. And this chromatograph, both the retention phase became a little bit more polar. So both the peak was eluted a little bit later, is delayed. So he found this sharp peak was switched. The first peak became sharp. The second peak became broad. So what does this mean? That means this sharp peak caused is not because of the sample itself. It's because of something else may be present in the sample solution. So he further studied this, then finally found he measured the pH of each collected fraction. He found a very, very interesting way. We can see this line. This is the pH. He found the pH is a gradually drop. After the solvent front came out, the pH was gradually dropped. Then it was suddenly goes up during the sharp peak area. That means the sample solution must be contains something. Then he analyzed the early fraction by mass spectrum. He found that early fraction contains bromine acetic acid. That is acid was appeared there. So because the sharp change of the pH caused that sharp peak formed. So then he finally found the theory how this peak was formed. Because the sample solution contains the acid, when you elute it with the mobile phase is relatively basic, then it will be form a sharp border of the acetic border, like showed here. This border. This is a stationary phase, is a mobile phase. When the stationary phase was moving, it has a relatively basic condition. Then because the analyzer, so after because the up phase, let me get here is a is aesthetic condition. This is the basic condition. When the mobile phase was moving forward, it will be switched a little bit, then became the analyzer is a aesthetic compound. It will move down to the basic, because it became ionized, then they go to the aqueous phase. When this ionized analyzer was moving forward, then reach the acidic border, then it will be protonated, then go to the upper phase. So it will be form a circle during this sharp acidic zone. So it will, if this analyzer will be can form this circle during the acidic zone, they will be form a sharp peak. So otherwise, it will be have a normal bald peak. So he further studied this method. He added 3 acetic acid, 3 acid during the stationary phase. He called this 3 acid the spacer acid. One is the acetic acid, one is the proponic acid, and butyric acid. These 3 acids was added in the sample solution, and these 3 DNP amino acid, because we block this blocked the N-terminal of amino acid, so it's acetic compound, both 3. After eluted with aqueous solvent, he found first acetic acid will be eluted out, because this most acid compare this have lowest pKa. Acetic acid will be eluted first, then form a 1 pH zone. Then the proponic acid will be eluted, form a 2nd pH zone. Then last one is the butyric acid eluted. After this, then go to the normal mobile phase pH. So during each of these zones changes, all the 3 analyzed. This one pKa is between these 2 acids. Then it will be eluted as a sharp peak during the sharp change of this pH zone. This compound, the pKa, is between these 2 acids, so it will be eluted between this pH zone. The final one is pKa is bigger than butyric acid. It will be eluted last at this zone. So this is he called the peak sharpening technique. But this technique is useful to make the peak sharp. But more important application he was found later in here. When he increased the sample size, the previous slide we can see the sharp peak. The sample size is 6 milligram of each analyte. In here, he increased the sample size 100 times to 600 milligram. He found it very interesting. This sharp peak became a sharp rectangular peak between these 3 spacer acids. All these 3 analytes became a sharp rectangular peak. Also, this each rectangular peak have its own pH zone. So when he take out the other 2 spacer acids, only keep the 1 acetic acid, then these 3 peak will be eluted together as a rectangular peak with a very sharp border. When you see the pH zone, this zone is still keep same as before, but these 3 compounds will have its own pH zone. So this can be completely separated. So now I'm going to explain why this form this sharp pH zone. This is how the solvent system was prepared for this pH zone defining CCC. We make a two-phase solvent system. Here we use ether as an organic phase. You can use any other solvent too. So you make a two-phase solvent system. After separate this two-phase solvent system, you separate the upper phase and the lower phase, and put in different container. Then for the stationary phase, in here we use organic phase as a stationary phase. We add the TFA as a retainer acid. So we use aqueous phase as a mobile phase. We add the ammonia as a elute base. So in this case, the column, HPLC column, will be first. Oh, sorry. More. How to? So in here, the column will be first filled with the stationary phase, contains the retainer acid. Then after sample was injected, this will be eluted with the mobile phase, contains the ammonia as a elute base. So after the equilibrium was formed, the first retainer acid will be formed a sharp pH zone, will be moved consistently from starting point to the from head to tail. So when this sharp border was moving, the second lowest pKa compound will be form a pH zone eluted immediately after this retainer acid. The iron circle is as showed before. It will, during each border, it will be form iron circle. So the second low pKa compound will be eluted next to this one. Then the low, the second high pKa compound. This is the highest pKa compound will be eluted last. Then all those pH zones will move in constantly pass through the column. After elute, you will get this chromatogram. After the solvent front, this zone is formed by the retainer acid. This is a TFA zone. So after TFA was eluted, this is the sharp zone for the retainer acid. Then the first lowest pKa compound is eluted out. Then it will be form a plateau is consistent pH zone, because this zone is determined by the concentration of the base, eluted base in the mobile phase. So this concentration, this concentration for this zone is the same as the concentration of the compound you add in the mobile phase, the basic eluted base you add in the mobile phase. So it forms all of these three compounds. It forms three zones. Each compound has its own pH, special pH, during this solvent system. So this method is a separated compound. This separation factor is determined by two factors. We know normal CCC separation factor is mostly determined by the partition coefficient between the two-phase solvent system. In here, now the partition coefficient is also important, but in here another factor was also in fact this separation is the pKa. So pH zone refining CCC actually they use two separation factors. One is the partition coefficient, one is the pKa, the compound pKa itself. So we come to the interesting application of this method. The first slide shows the separation of acetic dye. This dye, they call orange 5, is FDA approved compound. FDA approved dye can be added to the food. So actually this dye is not a single compound, it's a mixture of these three compounds, three acids. We can say the structure is very similar. So this is the HPLC. We can say these three peaks. After purified by pH zone refining CCC, this is a 10 gram the sample. I think it's 10 gram. I will check. 10 gram, maybe 5 gram. I will check more. Then this uses a normal 300 milliliter CCC. So we can see each compound form this is the pH, this is the UV, this big rectangular peak is the UV, this step by step one is the pH zone. In this study, I think we measured the pH by each cubes. You also can use the online flow-through pH meter to measure this pH. So for each zone, we analyzed the fraction by HPLC. You can see this each zone is a pure compound. So the small impurities was focused on the border of this zone. Oh yeah, that was 5 grams. This chromatogram is the same as the previous one. We can, in here I want to show the pH zone refining CCC can handle the different size of samples. This first one is 350 milligram, 1 gram, 5 gram. So with the increase of the sample size, the mixing zone for each is almost the same, but the pure fraction of this pH plateau is getting broader. That means with the increase of the sample size, the sample, you get the more purified sample because the mixing zone is almost similar. So you increasing size, the sample yield getting higher. That is one of the good advantages for pH zone refining CCC method. They like to handle the larger scale samples. So we can say the most commercial available CCC, they have upper limit. They give the upper limit of the sample scale. So the most of this record was made by this method. This when the pH zone refining CCC was found, the first was found for the separation of the acetic compound. Then we think this method can also be applied for separation of basic compound, especially the alkaloid from natural product. Then when we presented this idea to Dr. Ito's boss, Hank Fields, he was a natural product chemist 20 years ago. He have a lot of natural product crude samples. Then he found a sample, he said, contains these 3 alkaloids from his old box maybe about 20 years ago. We used. Then we use this pH zone refining CCC. In this case, we also use the organic phase as a stationary phase in this chromatogram. So we add the retainer base, not the retainer acid. If you separate acetic compound, you add the retainer acid. In here, we add the retainer base. We use the triisoamine as a retainer base in this case, and eluted with hydrochloric acid. So we can see this can be clearly separated into three zones, 3 pH zones. Then we analyze each zone, we get this pure fractions of these 3 compounds. Also, we can find, because this is use the aqueous phase as a mobile phase, it's similar like the HPLC, reverse phase HPLC. So we call this reverse displacement model. And so in this case, we use the aqueous phase as a stationary phase, eluted with organic phase. So in here, when the fraction was eluted as a salt, alkaloid fraction was eluted as salt. In here, the upper phase is the mobile phase, so we got the free base alkaloid. So you have a choice for these 2 methods, depend on how you want this your compound. You want the salt, you can use the aqueous phase as a mobile phase. If you want the free base, you can use the organic phase as a mobile phase. Also, it's because some alkaloid is stable in salt, you want to use this method. If it's stable in free base, you want to use this method. So you have choice to select the mobile phase. This is the application for separation of the modified peptide. We block the one side, the N side of the tripeptide. Then this will become a free acid. The one side have a free acid. So this peptide, protected peptide, can be separated by pH zone refining CCC. We can see this. Each peptide have its all pH plateaus. This is a partition coefficient without the acid and base. We can say this 2 was switched. According normal CCC, this one may, according this partition coefficient, this peak may eluted earlier. But in the